Hello again, everyone. It's time for ANOVA, the analysis of variance. This is possibly the most common test statistic that you might use. Of course, it depends on the type of data that you have, but if it is, if you have multiple groups, if you have more than two groups, as is often the case, you don't always have just two groups, control and experimental group, or placebo group and experimental group, whatever. You typically have several groups, and you're trying to see if there are differences among those groups, and if so, where are those differences at? But this test statistic, the ANOVA, will as we'll see here, it analyzes variances. It analyzes the variances between your groups compared to the variance within your groups. Okay, and if the variance between your groups is greater than the variance within your groups, then you have a significant difference somewhere among your groups. And so that's what the one-way ANOVA is all about. There is not enough. Basically, this course is not designed to get into higher levels of ANOVA, such as what's called the factorial ANOVA, that would be for an experimental design, a research design involving more than one independent variable. The one-way ANOVA, is really stripped down, very simple. One independent variable, one manipulation, and that's really what we've been dealing with so far for the t-test as well. One manipulation and comparing just multiple groups, more than two groups for one manipulation. So if your manipulation is, different treatment levels, okay, so you have a control group that maybe gets no treatment at all, maybe they just get a placebo. Another group gets, 50 milligrams. Another group gets 100 milligrams. Then that's three groups. You need an ANOVA for that. Okay, it's a one-way ANOVA. And it allows us to test for differences among two or more means. I say two or more here. You can certainly use the ANOVA instead of a t-test if you wish, but they're perfectly comparable tests in that case. But people do typically use a t-test if they have two means that they're dealing with, two groups, and an ANOVA if you're dealing with three or more. So as I said, you're comparing the variance between groups to the variance within groups. So you might ask yourself, why not simply use a bunch of t-tests, okay, to assess a difference between every possible pair of groups? So, for example, let's say, again, you have three groups, control, placebo versus 10 milligrams versus 50 milligrams, okay? Let's say that those are your three groups. Why not just compare placebo with 10 milligram, placebo with 50 milligram, and then 10 milligram versus 50 milligram. Okay, why not just run three t-tests instead of using a whole new test statistic, the one-way ANOVA? Well, there are four problems with just running a bunch of t-tests. Number one, you'll have a large number of comparisons. You only have three if there are three groups, but obviously the number of pairwise comparisons, as they're called, the number increases greatly as you increase the number of groups. For example, you have three t-tests you would need for three groups. Well, there are six t-tests you would need for four groups, okay, for every pairwise comparison. One t-test for every pairwise comparison. Also, the t-tests are not independent anymore because you're comparing, group A with group B, and then group A with group C, and then group B with group C, okay? So some of the groups remain the same between your comparisons. That's not a good thing. You're increasing the probability of a type 1 error. So what does that mean? That means that for every t-test that you run, you're setting your alpha at 0.05. That's fine for each individual test, but when you present your results, the assumption is that your alpha is at 0.05 for your overall analysis when you're taking into account all of your groups. That's not the case if you run a bunch of t-tests, okay? Because let's say, again, you have three groups. That requires three t-tests to get all the pairwise comparisons. And, so you're running three t-tests with alpha of 0.05 for each one. So in the end, you actually have more like alpha of 0.15, okay, 0.05 plus 0.05 plus 0.05. So your alpha is increasing, okay? In other words, you have an increased probability of a type 1 error what that means is, if you have an alpha of 0.15 instead of 0.05, well, you're more likely to reject your null hypothesis. Okay, if you end up with a p-value of 0.14, normally you wouldn't reject your null based on that, but with a bunch of t-tests and a higher and higher alpha level, you can reject it, okay? But that rejection is going to be more and more likely to be a type 1 error, a false rejection, where you would reject the null when you really shouldn't, okay? Where there really isn't a difference among your groups, but because you're just hammering away with these multiple t-tests, you're just more and more likely to just by chance find a difference, okay? You don't want that. You want to set your alpha at 0.05 and leave it there. You can do that with the one-way ANOVA. Also, another problem with running multiple t-tests is that, well, hey, you're running multiple tests instead of just having one test for one hypothesis, okay? So what the one-way ANOVA does is it says, okay, my hypothesis is that there is some difference among my groups somewhere. The null hypothesis is that there is no difference among the groups anywhere, okay? And that's pure and simple. You only need one test statistic for that, okay? The one-way ANOVA. So what you need to do, the logic of the ANOVA here, you obtain two estimates of the population variance, okay? One is based on the variance of your means, okay, the mean of each group that you have. Again, let's say 3 groups, the mean of each group. And another estimate of variance based on the variance of the observations within the groups, okay? So you have the variance estimate for the observations within each group. So between groups versus within groups, that's what it's all about for ANOVA. So both of these estimate the population variance if the null hypothesis is true, but they estimate different quantities if the alternative hypothesis is true. What that means is that if the null is true, if the null hypothesis is true, that means there is no difference among your groups. That's essentially the same thing as saying that the variance of your sample means is not different from the variance of the observations within your groups. That essentially they're all coming from the same group, okay? You don't have differences among groups, you just have one big group. That would be the null hypothesis, but if your alternative hypothesis is true, that there's a difference somewhere, that there's at least one group that's different from at least one other group, then that would make the variance of your sample means different from the variance of the observations within the groups. And I promise I'll portray this for you in a moment so you can kind of see what this looks like with some bell curves. So what you do with the ANOVA is you form what's called an F ratio. Okay, so here instead of dealing with a T, you're dealing with an F. And you can flip to the back of your textbook and sure enough there's an F table. It might be the last table that you have, although you probably have a chi-square table in there as well. Anyway, we've done Z, T, and now F. So the F table, you're going to need 2 degrees of freedom, which I'll get into in a moment, in order to look up a critical F value. But it's just like the T, just like the Z, you're getting an obtained test statistic, obtained F in this case, and you compare that to your critical F from the table. And if your obtained F is greater than your critical F, then that means P is less than 0.05, and you can reject your null hypothesis that there's no difference among the groups. So F, you're expecting, should be approximately 1, that there is a 1-to-1 ratio of the sample mean variance and the observation within groups variance. 1-to-1 ratio if the null hypothesis is true. Essentially, again, it's saying that all your observations apparently are coming from one big group instead of there being multiple groups. F should be larger than 1, significantly larger than 1, if the alternative hypothesis is true, if there's at least one group that's different from at least one other group. So you reject the null hypothesis if F is larger than or equal to a critical value, the critical F. Okay, some notation here. You have to be careful because now N is standing for something a little different than before. N used to be just the number of people that you have, maybe the number of people you have overall, the number per group. Here it is specifically the number of observations per group, okay? It's little n, okay? Big N would be the number of people you have overall in your experiment. Little n is the number of observations per group. And J, here's something I think is new at this point, is the number of groups, okay? Overall n is n times J, okay? That's little n times J. That tells you how many people you have overall or how many observations you have overall in your study. Two sample variances, as I mentioned. One is based on group means. It's called the between groups variance. And it is computed by the variance of x bar, and you multiply that by n. Your textbook gets into this in greater detail, so please do check out that chapter on Way ANOVA to see the detailed formulas here. But what you're getting here is mean square between, okay, and that is n times variance of x bar is, again, mean square between. Essentially, you're doing sums of squares between the each group mean and the overall mean across all of your observations. Okay, so you use sums of squares, multiply by n, you get mean squared between. The other variance for the F ratio is based on scores within groups. You compute variance of observations within each of the J groups, and you average those J values of the variance, and what you get is what's called variance, the pooled variance. Okay, another way of another term for that is mean square within. Okay, so your test statistic, your F ratio, F equals mean square between divided by mean square within. So what you're hoping for, based on your alternative hypothesis, is that mean square between, basically the distance between your groups, you're hoping that that's going to be greater than the variance within your groups. Okay, I'll show that to you, I promise, on the next slide here. So again, your hypotheses, the null hypothesis is that all your groups are equal. Essentially, they're all coming from the same group, one big group. You don't really have different groups according to the null hypothesis here. The alternative is that you have some difference, any difference anywhere. It doesn't matter which group it is, you're not getting that specific. You're just saying that I think one of the groups is going to be different from at least one of the other groups. Okay, finally we have a graphical depiction of this. Okay, so again, you're starting with the alternative. Well, let me actually jump down here. So the null hypothesis here is that all your groups are equal. Okay, they're all coming from the same bell curve. Well, this is more interesting, of course. Your alternative hypothesis is, and this is just one way of describing it, it could be that your third group is different from your from group A, group 1, group 2. Maybe group 1 and group 2 are not significantly different. Maybe these are overlapping so much that it's basically like this, and you say, well, they're not any different, but hey, boy, group 3 sure is different. Okay, you wouldn't say that specifically in your ANOVA alternative hypothesis. That's too specific to say that group 3 will be different from group 1 and group 2. Rather, you would just say there's some difference somewhere. Now, when you have a real hypothesis, that's not going to be specific enough. If you want to go ahead and say, I think that, so let's say that this is the placebo group, mean 1, mean 2 is the mean of your 10 milligram group. Let's say you're not thinking that there's going to be any difference there, that 10 milligrams is just not enough of your treatment, not enough of your drug to have any effect on the headaches. Let's say it's a headache drug. Placebo versus 10 milligrams is not going to be a difference there, but you're saying, wow, 50 milligrams, that really should create an improvement in, getting rid of headaches. Okay, so let's say, and that's a reasonable hypothesis. Well, as you'll see later, you need something in addition to your ANOVA. So you start with an ANOVA. You start with an ANOVA to eliminate the null hypothesis. And let's say you're finding this pattern, you need to do an additional step. It's called a multiple comparison procedure to do this comparison specifically and say, okay, well, I found a difference somewhere based on my ANOVA, but let me see if it's this exact difference here that I predicted. Well, you need a multiple comparison procedure to compare this mean with this mean, and then compare this mean with that mean. Okay, you want to say the 50 milligram group did better than placebo, and it did better than the 10 milligram group. That requires a multiple comparison procedure, which we'll see with the next lecture, actually. Okay, degrees of freedom for the ANOVA. There are 2 of these now, so you have a between degrees of freedom, which is simply the number of groups. In this case, my example was 3 groups, minus 1 is 2. So degrees of freedom between is 2. You need that for the table in the back of your book. You also need degrees of freedom within for that table, which is n minus j. So this is capital N. This is the overall number of people or observations you have in your study, in your experiment across all your groups, minus the number of groups that you have. Okay. And this is the last slide I have. I don't have an example to work with here in terms of crunching the numbers, but please do refer obviously to the textbook for some examples here. I just want to tell you how you can write this up based on APA style. There was a difference among the groups. This is always what you're hoping for, such that F, and in parentheses you always have degrees of freedom. We've seen that before with the t-test, except now instead of just one number for the t-test, you have two numbers for the f-test, because you have 2 degrees of freedom. You always put degrees of freedom between first, so in this case 2, comma, degrees of freedom within. So let's say you have 3 groups of 20 people each. That's 60 total. This is overall n, which is 60, minus the number of groups, which is 3. 60 minus 3 is 57, so it would be 2, comma, 57. Okay, and you would use those numbers, look up your critical f value in the table in the back of your book. But this is not the critical f value you would write down. This is the obtained f you would get from your formula of mean square between divided by mean square within, or just get SPSS to crank it out for you. And the p-value tells you, hey, you compare that to your alpha value. Okay, you're hoping that that's going to be less than 0.05. If it is, it means that your obtained f, which you write here, is greater than your critical f. You don't actually write the critical f anywhere in your results based on APA style. Okay, but here's that next step I was talking about, where you need multiple comparison procedures right away to see where your difference is. It's important to remember that the ANOVA simply tells you that you have a difference somewhere in your groups. You don't know where the difference is. You can't really describe the difference very well at all without doing that next step of multiple comparison procedures, which I will get into in the next lecture here. But you would put pairwise comparisons with the Tukey procedure, and that's just one of several MCPs, multiple comparison procedures, that you have to work with, but it's a good one. The Tukey procedure revealed that the X group, whatever, with that mean and standard deviation, scored significantly higher than the Y group with that mean and standard deviation. And also the X group scored higher than the Z group with that mean and standard deviation. So there was no difference between the Y and Z groups. And this is just one of many possibilities, but this is equivalent to what I described before, where the X group is your 50 milligram group, and it did better than your Y group, which is your placebo group, let's say. And the X group, your 50 milligram group, also did better than your Z group, the 10 milligram group. Okay, and there was no difference between your placebo and 10 milligram groups. That's basically what you're describing here. So the ANOVA requires you to have a lengthier results section because you're describing where are the differences and where aren't there differences among all of your pairwise comparisons, usually what you're interested in. Of course, you'd be more specific with your labels of your various groups and specifying the dependent variable. That's also important. So you would ask, difference among your groups. Well, difference of what exactly? Well, difference in number of headaches, let's say. You always have to specify what you're measuring, the dependent variable here. Okay, so that's the last slide I have for ANOVA. Again, read the chapter in your textbook on Way ANOVA, and definitely focus on that and understand the differences between ANOVA and the t-test. And in just a couple minutes here, I'm going to record the lecture on MCPs, multiple comparison procedures, because that really is tightly linked to the ANOVA. Whenever you find a significant F value, your obtained F larger than your critical F, you reject your null hypothesis. You have P less than 0.05. You immediately then need to move into the territory of MCPs to find out what exactly is going on, which group is better than which other group. Okay, because it's perfectly possible. Again, let's say you're predicting that your 50 milligram group is going to be doing better than your placebo and 10 milligram groups. Well, maybe you'll reject your null, and so that is encouraging. It tells you that maybe you support your hypothesis, but you don't really know until you look at the, you have an MCP to really compare those means in terms of at a pairwise level. It's possible that maybe your placebo group did better than the others. Okay, maybe it's not likely, but that's possible. Until you run the MCPs, you don't know what exactly the pattern is. Okay, you might reject the null, but you can't yet say that you supported that hypothesis that the 50 milligram group did best. Maybe the null was rejected for the Way ANOVA because the placebo group did best. Maybe it was rejected because for some reason the 10 milligram group did best, okay? You just don't know until you run pairwise comparisons with a good multiple comparison procedure that controls for type 1 error rate and all that good stuff that I showed you before. So I guess I haven't pointed that out yet. The reason you want a multiple comparison procedure like the Tukey procedure is because it's better than running individual t-tests, okay? It's better because it doesn't violate those assumptions I mentioned before. It doesn't increase a type 1 error rate with every comparison. It takes all that into account, okay? Basically, it forces it to be more conservative than running a series of t-tests, okay? So this Tukey procedure is not the same thing as simply running a bunch of t-tests. It's more particular than that when dealing with a one-way ANOVA. Okay, so that concludes the lecture. Look forward to getting into MCPs next time.